Hi, and let me continue with the lecture about the bypass capacitors. And last time we checked the power supply techniques, how to how to stabilize the power supply voltage using bypass capacitors. And today we will continue this with the detailed overview of the capacitor technologies that are used for that, and a lot of examples of how to place bypass capacitors for efficient power supply bypassing. So bypass capacitors, today's topic. First, the efficiency of bypass capacitor regarding the high frequency voltage stabilization lies in its series inductance. The series inductance of the bypass capacitor determines the high frequency behavior. So we need high frequency at low impedance at high frequencies, so which this low impedance is defined as the omega L series, and here the impedance is defined as 1 over omega C. So here is the resonance frequency, omega S, which would be 1 over square root of CLS. Well, this series resonance frequency is also called the self-resonance frequency, and this LS is also called equivalent series inductance. So usually these the names are self-resonance frequency, and this would be also equivalent series inductance. The value which is the impedance which is reached at the self-resonance frequency is equal to the series resistance, which is sometimes or quite often called equivalent series resistance. So ESR, ESL, these are two main quality indicators of the capacitors. And at high frequencies, we are mostly concerned about that one. So the series inductance, or we already know it's ESL, is determined by different parameters. First of all, the size and shape of the capacitor, whether it's through hole or SMT, the size of the case, the type of the capacitor, what is the initial dielectric, is it ceramics, is it tantalum, electrolytic, aluminum capacitor? These are all have different properties. And how we place it, the position, the orientation, and the track length we use to connect it to the integrated circuit. These are three main groups of capacitors we use in power supply bypassing: the electrolytic, tantalum, and ceramic. Electrolytics have the larger capacitance, the aluminum electrolytic, and they are a little bit larger, but they have quite, let's say, quite low ESL and ESR, but not particularly very low because of the size. And they have low mean time to failure, which means that their lifetime is short. Tantalum capacitors are a little bit smaller, much smaller for that matter. They have still quite high capacitance values, and they can reach different ranges of equivalent series inductance and resistance. So they are very good, some of them not very. But they are very expensive. I mean, very expensive means still we measure this price in cents, but still they are much expensive than ceramic capacitors, which are the highest quality, the lowest capacitance values, very small, of course, very low ESR and ESL, and they have long lifetime. They are the best capacitors you can get in this range. All right. Standard aluminum electrolytic capacitors are mostly used for mains frequency applications. So the data which are given are for 100 Hertz. Why for 100 Hertz? Because the rectified sine frequency is 100 Hertz. It comes from 50 times 2. Now, the main quality parameter given for this electrolytic capacitor is so-called tangents delta. This tangents delta is the angle between the ideal angle between current and voltage, which would be 90 degrees. So if you draw here a graph of real imaginary part of the impedance, actually the imaginary part would be low. So the impedance would look like that. So we have a real imaginary part. So this is the real part, this is the imaginary part. Ideally, the capacitor would have the impedance like that. So this is the angle. This is the delta. Sorry, delta. And this delta angle is, I have to try to write it correctly. This delta angle, the tangents delta, would give you the quality of the capacitor. It's real versus imaginary part. And it should go to 0. So 0 would be infinite 90 degrees angle and infinite quality of the capacitor. Okay, so we know that tangents delta 0.2, 0.3, this means quite a bad capacitor. So you can have very good aluminum electrolytic capacitors that work up to hundreds of kilohertz, but that's more or less the limit of how far this technology can reach. The low ESR, so-called low equivalent series resistance, the channel capacitors are better in that sense. They are higher quality capacitors, and they already, besides the basic parameters like tangents delta and that stuff, they also have graphs. And these graphs would show you the impedance and the equivalent series resistance. And here we have two of the different capacitors, Tantalum capacitors. Okay, let me draw. Here is the 1 over omega C, here as well. This is the lower value, this is the larger value capacitor. And here we have the resonance, and here we have the omega L. Here is the omega L part, here is the resonance. So, and this is the equivalent series resistance. You see that it actually changes with frequency as well. So, these capacitors seem to be quite okay regarding the equivalent series resistance, going down to 10 milliohms even, maybe 20 milliohms here, which is very good. What about ceramic capacitors? Well, ceramic capacitors are could be found in two forms, as the others as well, the through-hole and SMT. And if you check their resonance frequencies, you see that through-hole capacitors have much lower resonance frequency than the surface-mounted. That's the reason is the size. The loop size is defined by the length of the capacitor, and larger capacitors have also larger equivalent series inductance. And since the resonance frequency is 1 over square root of CL, this equivalent series inductance, if this one goes up, the resonance frequency goes down. So here, since the capacitors are larger, the loop size is also larger, and therefore the equivalent series inductance is larger. So this is how different capacitors impedance looks like if the capacitors are in the same case, for through-hole and for SMTs. So they all have the same series inductance, omega L, but different impedance at low frequency, 1 omega C. So by increasing the capacitance, you get to lower and lower impedances. Of course, the resonance also shifts toward lower frequency, since the omega L is constant. But if you go to let's say from through hole, this is through hole, you go to SMT, the story is just the same, but the resonances are at higher values here and here. Why? Because ESL, the omega L here, acts has lower impedance. See, at 1 gigahertz it reaches maybe 10 ohms here, but here it reaches more than 100 ohms. So the ESL is 10 times larger than here, which for SMT capacitors. But even if you take SMT capacitor in the same case size, you also have different materials to choose from. So there are three main materials group: NPO, X7R and Z5U. These are the most quality capacitors. The resonance is most sharp. These are less quality, and these are the worst quality. See, the resonance is not sharp anymore. So let's go into details here. The COG or NPO ceramics, these are the best quality ceramics you can get, but these capacitors have low capacitance values in the same case size because the dielectric constant, the permittivity, is quite low. But it's very good quality, which means that the temperature coefficient is very, very small, so they are very stable in the whole temperature range. So you can use them to make oscillators, you can make different resonance circuits with them. They are intended more or less for high frequency, radio frequency and filtering applications because they are stable. Their value do not change much with the frequency or their properties as well. Because if you take them in different case sizes, you would see that their resonances shift a little bit, and that's because smaller capacitor has also lower series inductance and higher resonance frequency. Now, next group of materials is X7R or X5R. This is ceramics which has higher dielectric constant, higher permittivity. The capacitance values are therefore higher in the same case, but it's worse in case of the tolerance. The temperature coefficient is quite high, so they are not intended for very stable capacitance for filters or oscillators anymore. The values of the capacitances can be much larger, but their capacitance is also quite dependent on frequency, up to 10%. But regarding the case, their series inductance is in that range as well. So it's not much different than here. It's all more or less dependent from the case size. What about the Y5V or Z5U? These are two very, very bad ceramic, which has only one good property, that's the dielectric constant. The capacitors using these ceramics have the highest capacitance in the same case, but their temperature coefficient is really bad. And not also that, the capacitance is very dependent on the DC voltage. You see here, the capacitance is like dropping really, really fast with the DC voltage. So if the nominal voltage of the capacitor is 100 ohms, 100 volts, you see that it reaches only 10% of the initial capacitance as at 0 volts, which is disaster. But you can buy such capacitors and you should be careful when choosing them. Well, let's check here. 50 nanohenries, 70 nanohenries even, the series inductance. So why would someone buy such a capacitor in the first place? Well, because you get the highest capacitance in small case, but it doesn't help you much if the capacitance drops with voltage really, really fast. But then maybe the problem is not that it works all the time, so that the application may not be the one that it works all the time at high voltage. Maybe if you're using, let's say, 12 volts, you are here, or even, I don't know, here. So this will be 12 volt. So it will only lose 20% of the capacitance. But why would you then choose a 100 volt or 50 volt capacitor for 12 volt? Maybe because you have some applications where you have large voltage spikes that are due to some noise or disturbances, and the capacitor has to survive high voltage as well. So you would use that capacitor because it would mostly work at 12 volts, but sometimes you would get a very short voltage spike up to 50 volts and it will have to survive it. So in that case, such a capacitor might be a good option, and it's the cheapest you can get. If you compare X7R and Y5V versus the DC voltage, you see a big difference in capacitance. So be careful. Effect of case size. Well, the shorter the capacitor, the better, the lower the inductance. Maybe there are some cases you see here. These are classical shape, longer and narrower, but you can have the so-called landscape version when the capacitor is short and very wide, like that one, or even that one. Then you have interdigitated capacitors, which are more or less more capacitors in parallel, like that. And this would even decrease the series inductance. And there is a Leica form, which is the lowest capacitance possible. It's in a BGA format. So effect of case size. You have a so-called portrait and landscape configuration of capacitors. This is 1206 and 612. So here, this is the length the current takes from one terminal to another, and this is the length here. So wider and narrower and shorter would be better in terms of series inductance, and that's the difference here and here. So that's quite a lot. And calculating the series inductance out of it, you would get almost 1 nanohenry for 12.6 or even more, and half of that for 612. See? So that would, of course, with that you prefer wider and shorter case sizes for lower inductance. What else? Well, a classical multi-layer ceramic capacitors are made like that the plates are interleaved. So half of the plates are connected from one side, the other half from the other side, and then they are pressed together. So it's like interleaving contacts. And then when they are pressed, you get one contact here and the other there, and all the plates are then within connected in parallel. So here the current has to travel the whole path through it down. What about the Leica chip array? The Leica chip array has contacts on the same side. So the highest frequency currents just flow here and there. So it's much shorter path and therefore much lower series inductance. So checking all the inductances of the case could be done on that figure. Here I have the capacitance. Here is the self-resonance frequency. And here are the case sizes. Since the self-resonance frequency and the capacitance is related to inductance, these case sizes correspond to the same ESL, equivalent series inductance. Okay, so let's say we start with 0805, which is no normal case size, or maybe 0603, which is, I don't know, it's not anywhere. Well, 0805 would have a series inductance of around 1 nanohenry, and the self-resonance frequency of 100 nanofarad of such a capacitor would be in the range of 16 megahertz. Now, if you decrease the value, of course, the resonance frequency goes up. but you can change the case size, maybe using 0306, the landscape version. You would see that the same value of capacitor would give you almost 30 megahertz of series inductance of less than 500 pico, half a nano. But then going to interdigitated or Leica, you would get much higher. Of course, these are also expensive capacitors to use. What about tantalum capacitors? Well, these are, as I said, very good, but they have some issues, and these issues are two actually. They are polarized, and they are very unstable regarding the lifetime. So they are very voltage sensitive. So higher voltage or reverse voltage would break them immediately. They can explode very easily. So these are not very reliable capacitors. But nevertheless, they are still used, and but not very often, I must say. If you compare ceramic and tantalum capacitors, you see that they are of similar sizes. Maybe tantalum are a little bit larger. And they are rated to lower voltages. The range of capacitance is of course much larger, but they are polarized. And you have to take care how you turn them. And if you compare the ESR and ESL, you see that tantalum capacitors of course have a larger ESR and also larger ESL. That would then lead to a lower frequency range. But that's not a bad thing, because that's how you can choose what to use in your design. Because what you need in your design is of course high quality capacitors in the power supply arrangement, but then you need one capacitor which is not that high quality, which has to have a higher value, but maybe also higher series resistance to make the damping of the resonance circuit. And this could be done by a tantalum or even electrolytic capacitor in that matter. Okay, so the comparison of equivalent series inductance. The ceramic capacitors taken from that graph, and tantalum capacitors have higher series inductance, as you see here. They also have higher case size, of course. And their temperature dependence actually is even positive, which means that they work better at higher temperatures. Nevertheless, to wrap up here, I must say that ceramic capacitors are of course used for high frequency applications to bypass the power supply, and they should be placed next to the chip as close as possible. Then the electrolytic or the tantalum capacitors are used as a bulk capacitors to minimize the output impedance of a voltage regulators and to damp the resonance, the unwanted parallel resonances in your circuit. That damping can be achieved by choosing just the right capacitor which has not too high or too low series resistance. And the value of the capacitors of course should be much larger. How large? Please check out the previous lecture. But then we will continue on the placement of capacitors, because it's not just the capacitor itself, it's also how you place it. And here are two examples: the single layer connection to the IC or using ground planes. Ground planes are big planes of copper that can be applied in multi-layer PCB to distribute power or ground very efficiently. So the equivalent series inductance is more or less dependent on the loop size. So this would also define the ESL here, and that loop size would define ESL as well. So how you place it, how close you place it, and how you connect it would define the equivalent series inductance of capacitors. So first we have to identify the size of the loop. And there are some empirical equations and web calculators for that. So this is the square loop size. And here you can calculate the inductance of such a loop. Well, if you have a long rectangular loop like here, you can also calculate the inductance differently. If you have such a square-like loop over the ground plane here, then it behaves like a double height square loop. So the same equation goes here, but you have to use the double height. If you have one single wire or track over the power plane, this is the equation, how to calculate the inductance of that wire. The width or the width of the loop can be determined by measuring the distance between the connection points. If these are wires or connections to the rest of the circuit, this is how you can measure and determine the width of that loop. And the height of the loop, that depends on where the ground plane is. So this is the ground plane, this is the power plane, and this is the height of the loop over the ground plane. But calculating that would require taking twice of that height to get the area of the loop. Of course, we don't have round wires on the PCBs, we have square-like or rectangular actually. So this is how you can translate from the width of the track to the diameter of a wire, because this is then used in these equations. So let me show you two examples. First is using this integrated circuit and putting a bypass capacitor. This is a very, very standard digital logic integrated circuit. And usually it has power and ground somewhere on the opposite sides. This comes from a two-sided PCB's story where the connection of ground and power supply was the easiest by having this pin arrangement. But for a bypass capacitor, it's very, very not appropriate, because you see how the loop size is. Actually, you can represent that loop as a square-like loop of that size, which can be then using to calculate the inductance of that whole connection of this bypass capacitor, and it's in the range of 30 nanohenries, which is a lot. Well, 30 nanohenries doesn't help you that much if you choose a very good capacitor or very bad one, because the difference in inductance would not be a big one if you already make such a big inductance using this loop size. But of course you cannot make it much smaller, because this is the size of the loop you get if you connect it on one single side according to this pin arrangement. Of course, if the pin arrangement would be different, the loop size would be smaller as well. So this is the responsibility of the manufacturers of the integrated circuits, to arrange the pins in that way that you can attach the bypass capacitors to make smaller possible loop sizes. If you use power planes, then you can just put wires here and here and connect to both power planes and connect with wires here. And if the inductance between this point and that point is very low, if you have a ground plane or power plane of a large size, the inductance of that plane is very low. So it even doesn't matter how far from this integrated circuit you put this capacitor. Well, that's just in theory. Of course it matters, but less than if you just use tracks to connect them. But if you calculate it, you have to calculate two areas. That one, if you think of this as a ground plane, you need this area, and here as well. And calculating the inductance from these dimensions here, you get 4 nanohenries for this capacitor and 25 nanohenries for this loop area here. So not a lot better. Actually, they're almost the same, even though we used power planes. So that's the idea then, how and why you need a better pin arrangement if you want a high frequency bypassing to be efficient. And first of all, you have to connect the capacitor as close as possible, which means that you have to shorten the length of the tracks. Maybe don't put just one wire, put more wires to make it even smaller, the connection inductance. And here is the example of an SMT capacitors with additional length of wires, and here are the series inductances. So by the E probably is the worst one. It has the longest and the narrowest wires or tracks, and the A is the best one, which has no tracks at all. It has lots of wires on each side. So if the reached or the achieved series inductance is very low. So let us go a little bit into practice, right? So we know now approximately what kind of inductances we can expect from the cases themselves and also from connections. So a 2-layer PCB and 4-layer PCB will be compared. So the 2-layer PCB, you know, it has only 2 layers, top and bottom, and these are the realistic thicknesses. So 1.5 millimeters is the thickness of the core. And this is a 4-layer PCB, which has 2 intermediate layers, from which one is on the ground completely and the other is on power completely. And the wires are through-hole wires, so no blind or buried wires are here. So on a 2-layer PCB, the ideal placement would be like that. So you have a very, very short connection to both pins, and you have ground plane below, and you can connect to the ground plane via wires. So let me just select the color. I will use orange here. So this is the loop size. We are just talking about high frequency loop. So how does it work? This is the capacitor. These are then the tracks. So they are representing a small inductance. And this is the loop size. It should be this as small as possible. So taking the tracks together would make the loop size smaller. But then if you look from this side, you see that you also have a ground plane below. So I put a wire here, as close as possible. But then if I have a ground here and there, it doesn't hurt if I put wire here as well, and then the part of the current would also flow on the ground. Maybe like that. And that would even decrease the impedance of the ground connection. The power should be taken to the capacitor, not to any other point. Because if you connect the power from here, then this inductance will be connected in series to the capacitor from the perspective of the power connection, which means that some of the noise of this current flowing through this track would be then also transferred to the power line. So the equivalent circuit would be like that. So this is the microcontroller, whatever that is, and the power supply and the ground pin. There is some inductance, of course, of that connection. Then the capacitor itself, then the inductance, and the inductance of the wires. Here it goes to ground. This is the ground connection. Here the VCC comes from. And now, if you connected the VCC, here is the high frequency loop. So if you connected the VCC here, then you would get this noise also present to the VCC because of the high frequency current. Now, the delta this is delta I, the change of the current in time. Now, of course, I also put a ground wire here to make a very, very small inductance. I will make of the ground plane between both grounds. So that would decrease the impedance of this side of the loop even further. So this is how that placement then looks like in 3D with the real dimensions. So that's the loop size here. of course you have to account also for the leads all the way down to the chip. And the power comes from here. The ground also has this row. So this is another connection on the ground, which is better in terms of the impedance. Here is the impedance, of course, of the wires, the inductance of the wires, but inductance on the ground plane is very, very low. So this is then connected in parallel with the ground connection. What about 4-layer PCB? In the case of 4-layer PCB, this would be the ideal arrangement. Again, the loop size is the same. That's the high frequency loop size. All the high frequency current flows here, doesn't flow further. And the connection of the ground and VCC comes from the single side. So the loop size is still on a single side here. That's the loop size. And this is the connection of the ground and the power coming from a wire. Alternatively, if you cannot afford the bottom layer to be used for ground all the way, you can connect both on top as well. And that wouldn't even hurt a lot, because the VCC and the ground are connected in the same manner. So that's the loop size. Not different from before, not much. But here the ground and power supply are taken from the same layer. And the loop size looks like that. Again, very small. And since the power and ground are taken from the same side, but to the capacitor and then from capacitor to the chip, it is very efficiently also in terms of the noise transfer to the rest of the circuit. Because if you are having a very noisy circuit here, that's the microcontroller. That's the microcontroller, very noisy. Then you connect this capacitor here. And then you connect from capacitor further to plus and minus. You see that all the noise that flows here would stay there, and you would get almost none further towards the circuit. Since these inductors here does not change much. But if you connected power supply there or there, you would get all this voltage and be transferred towards the rest of the circuit. Well, on the 4 layers, you could also do that. Actually, you could put a bypass capacitor almost anywhere and connect the pins to power supply and ground plane. So the loop size now is that one here, but not just that, also in 3D. So maybe it's better to look in 3D. So this is the loop size then. That one. Vertically, and here also vertically, sorry. Down here and that. They're triangular shape because here it connects to the power ground and here it connects to the power and here as well. But these are the loop sizes. All the rest doesn't matter. All the rest is the impedance of the ground plane and the power plane, and it's very low and we just neglect it in the first approximation. Of course there also adds to it, but it adds less than a wire. So this would be also an option. What else? Well, you can put capacitor on the other side, like here on this 2-layer PCB. So the loop size would then be like that. It is larger. So it's not as efficient as if you put it on the same side, but it takes much less space. So you can easily route out any tracks you want. But then having capacitors on bottom layer would require 2-step soldering process, which of course can cost money. In 4 layers, it is a little bit different because now the capacitor connects to here. This one connects to here, and then this is when the power enters from the power planes, and then this extra connects there and extra here. So the connection of the power is not now directly to the capacitor, but somewhere in between the tracks from capacitor to the chip, which of course it's less convenient than this way here. This one, in terms of noise spreading around, is better. But this one has lower impedance because there are planes that helps here. Okay, what about the parallel resonance with copper planes? What does it mean? Well, the thing is that here we have a capacitor with such a loop size. But then you have a capacitance also between the power planes. And this is a very, very good power plane capacitance, which is much, much better than any capacitor you can get. So what do we have at the end? We have our capacitor, and in parallel we have the capacitance between power planes. And since that one and that one are very different in terms of the ESL, ESL, and also the capacitance itself, you can get unwanted parallel resonances. And that's what you get. If both all capacitors are very good quality capacitor, then you can get unwanted anti or parallel resonances. So this is a power plane capacitance, power plane. Of course it drops. Here is the, because it's much larger, here is the bypass capacitor capacitance. Then it has its own series resonance, omega series of the bypass capacitors. Here we have omega L, ESL, L, if you want. And now it reaches the resonance, parallel resonance between the CPP and the LESL, which means that you have this situation. C bypass and L bypass in parallel with the C power plane. Now this capacitance together with that L bypass forms a parallel resonance circuit. And this is the resonance of that circuit. And of course the frequency of the resonance depends on the bypass equivalent series inductance. But you have to be aware of that, and sometimes it will just hit directly the frequency which is the disturbing frequency in your circuit, and you would get a problem because your power supply circuit will have a resonance just at the frequency when you don't want it. So let me finish this lecture with a few examples. First of all, the two-layer PCB. This two-layer PCB has a microcontroller, and that microcontroller has several bypass capacitors. Here, 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 and there, and there. All that capacitors are placed in different ways. Not all of them are optimal. First of all, you have to know that I used special, so I had enough space. So I used a big ground plane bottom layer, and I used also a ground plane or power plane on top. Even though I have only two layers, I just had a power plane on top. So the capacitance of this plane here, which is connected to the VCC, is in range of 4 picofarads, which is very, very low. Of course, having such a low capacitance is not very, very beneficial for the power bypassing, but it's a very, very high quality capacitance, which may even, as you've seen before, it may help at high frequencies, or it may also cause trouble due to the parallel resonances between these capacitors and the rest of bypass capacitors. So first of all, let me show you this capacitor. That capacitor is placed not optimally because the tracks are quite long. They could be lower. And the power is taken from this side. So the noise that generates here on that inductance is then transferred to the power supply directly. And the ground is connected from this side, but it's not connected to bottom ground plane. So bottom ground plane has no effect here because it's not connected. So the equivalent circuit of that capacitor would be like that. So that's the microcontroller. That's the current source the microcontroller actually represents. And then the ground, that's the impedance of that ground connection. Here is the capacitor. Impedance of the power connection, here, that one. And then the power comes from this side. The ground comes from there. So you see that all the high frequency noise that is actually taken from the capacitor, which provides a voltage drop on that inductor, then also adds to the noise of the power supply. So it's not a good idea. It would be better to connect the VCC from other side and to utilize the ground plane if we have it. So I would certainly put this capacitor closer, put a wire maybe there, a wire also there, to make the connection bottom side as well. What else? Well, maybe one thing, you cannot put these capacitors extremely close to the microcontroller because they would just not fit, and they would probably be as an obstacle to other connections which go out of this microcontroller. What about that one? Well, here the ground connection is very short, which is good. The power connection is a little bit longer, but what troubles here is the connection of the power, which connects just in the middle of that track. Connecting to the middle of that track would mean that you increase the inductance of this connection because you put a hole in the connection directly here, so the inductance is increased. But more importantly also, the power is taken to it here at the middle of this connection. Why is that a problem? The same as before, actually. This part of the inductance here then is connected in series with the power supply, and that's also a cause of the noise going further to the rest of the circuit via the 3.3 volt power supply. Now, if you have an option of choosing shorter ground or shorter power supply connection, I would always go for shorter power supply connection. And what is the reason for that? The reason is that on the ground you also have usually an option connecting via the ground plane, and this is a low impedance connection. So maybe you can afford a longer distance here and a shorter on top. So like here, where this connection is the shortest there is probably, and here on the ground you have connection on bottom layer as well, which then acts as a parallel connection to the top. And therefore I put two wires, one here and the other there. Okay. And the power here is still connected just from the microprocessor side, which is not an optimal solution, but sometimes you don't have others. And here there is a wire put on the ground connection here. I wouldn't put a wire in the connection between this and that one. I would keep this connection as clean as possible without holes, wires and other obstacles. I think the optimal arrangement is here. So we have a tantalum capacitor, we have a ceramic bypass capacitor. The 3.3 volts is the closest there is. There are two wires, one here, one there, connecting the ground connection as well. And we have power connected from the 3.3 volt connection from here. First to this, bulk capacitor that also stabilizes the parallel resonances because it's not the highest quality capacitor. And then continuing to here, and this is the high frequency part where this area size determines the equivalent series inductance of that capacitor. This would be the most appropriate connection of a two-sided PCB. What about four-sided PCB? For four-layer PCB, not four-sided, four-layer PCB, Well, this is an example. We have a lot of bypass capacitors all around this microcontroller. Here we have a lot of ground connections. All this bottom part here is a ground and goes to this, that, and other pins which are here. And this is also a power pad. Now, all the power is distributed on the second mid layer and all the ground on the first mid layer. On top and bottom we have tracks. So let me show you the top part first. Okay, on this top layer we see all these capacitors, and they are connected with the wires to the mid planes. And they are directly connected to the 3.3 power pins here and here and there and there. There are several power supplies. Actually, they are here. There is the VDD 3.3A. This is the analog part. This is the digital part. And there is, I think, also the core voltage, which is 1.8 volts. Nevertheless, the top connections are here. These are all 3.3 or power connections. The ground connections are on the first mid layer. So these are the ground connections now. You see a problem here. Well, I see it actually, and I think you will see it immediately. So these are the 3.3 volt connections. The ground connections then have to go here and they define the loop area. Of course, these wires are interfering a little bit, but there is space left between them so that the current can flow through it. But then there is a problem here. This track is cutting the ground plane, and therefore this current cannot return back shortly to these pins here. So it has to go around and there, and here around and there, which makes the loop much, much larger. There is not such a problem with these capacitors here, or there, or there, or there, or there, or there, or and so on and so on. This ground connects easily to these pins, but here this track is just not appropriate. So we will have to remove it, and I will show you later. The next layer is the power supply layer. This is the 3.3 volt power supply layer, and this is the analog 3.3 volt power supply. And this track actually connects the connection called VDD core to here. So this track could be easily placed on that layer, and that's what I actually did at the end. So, and now the bottom layer. This is the bottom part which contains some tracks, but also the rest of that layer is used for ground plane as well. So use as many layers as you can for ground plane layers, because that would make the ground really well connected together, and that would give you much less, would represent much less problems with the EMC. More ground and well connected to each other would make the impedance of the ground very low. That would first of all cause less common mode noise because of the current generated common mode. But not just that, they would also decrease the loop sizes and the impedance for all the bypass capacitors you have. So about this track, which makes a lot of problems with this return current path for these capacitors, it could be easily removed from this layer, and now this connection for this capacitor would be direct. But please note that by designing it, you have to make space with these wires. And since all wires are through-hole wires, they are taking a lot of space in planes. And that's one of the reasons why you should use maybe blind or micro wires. If you have a lot of these wires, they would really make your plane as a Swiss cheese, which would mean that they might even take too much space. Like here, if you put these wires closer together like that, then the ground plane would be broken. And then this current maybe would have to go around it. And that's not good. And finally, if I put this track to the power plane instead of here on this ground plane, then this track wouldn't make any problems, because now this cheesy plane here actually doesn't have any role at all because it's a power plane. It delivers power to these wires here, which then deliver it to the upper layer and to the microcontroller. And here are the bypass capacitors. I think it's quite optimal arrangement. Maybe it would be even better if I put these bypass capacitors on the bottom layer, but that would require two-layer placement of the components, and that's what I didn't want. What about this example here? It's just a quick example how the bypass capacitor, if placed wrong, would be so bad that this design even didn't work. So what was here? This is the bypass capacitor. This is the power supply connection. It's quite okay, I would say. This is the ground, and that ground actually should be placed here. But actually it was using a wire going to the bottom layer, coming here, going to the top layer, going there, and to this track. It was too long, and this controller for this switch mode power supply did not work at all. It was just not working. So when we used a short wire connecting to this, making a bridge, it started working. What else? This is a beginner's mistake. It's one design that one guy brought to me and asked why it doesn't work. Well, you can see by yourself quickly what's the problem. The problem are these capacitors here connected in parallel. You see, all these capacitors are connected in parallel, and then there is one track going here and here and there to all these pins which are intended for power supply. So that controller and all the others which have several power supply pins do not have them just like that. They have them to make the power supply possible to operate. So if a microcontroller has a lot of power supply pins, they are always placed in pairs next to each other. And the reason why they are placed like that is the following. Because you cannot achieve low impedance at high frequencies, which means low ESL at high frequencies. You cannot achieve it just by using one capacitor. You need several capacitors. And therefore you have as many power supply and ground pins that you are able to connect them optimally, each one next to each pair of power supply and ground pin. Like that. So that guy actually did just the opposite. He put them all in one place and connect them with a single wire. So that mistake actually was not the only one. The other one does now pay attention. These capacitors here. This is the ground, I think. I'm not sure exactly. I think this is the ground wire. Yeah, I think so. Let me see. I'm not sure, but nevertheless, if it's on one or another side, if you check on bottom, there are a lot of tracks that are breaking the ground plane below, and these are the wires here that connect to the ground of that controller. And here these are the capacitors here. And now the ground is broken. You have to go around here, back here, or maybe all around there. I don't know how far away to come. No, here. So that's the circuit actually worked, but not very well. This is the measured the measured near field magnetic field because of these capacitors. The current loops were large and they were also radiating a lot. Now, the last example is this switch mode power supply, and as you know, the highest current spikes that they have to be sort of minimized are here, charging this capacitor. So this capacitor should have the lowest ESL possible to make flat output voltage. So here the question is how to connect this capacitor, and you all know that it should be connected now to a single point on both sides and then taken voltage from these points further away. But the actual design was like that. So this is this output part, the diode, the current, the capacitor. So this is the diode, this is the capacitor, and this is the track. And the voltage was taken from here and taken out. So this is the part of the series inductance, this part here, and these high current spikes running through this caused a voltage drop on this inductance. This voltage drop was then taken outside. And as a result, this was the radiation, quite large. I think I already showed you that, but nevertheless, it doesn't hurt if you see it again. Also at higher frequencies, it was present up to 40 megahertz. So in terms of conductive electromagnetic noise, we don't see a big issue here because the problem is at the output of the SMPS, not at the input. So let me show you what did this capacitor do. So that was the noise because of that capacitor. Here, this short piece of track actually caused so much noise at the output. And this is the resulting near magnetic field. If we added additional capacitor here, which was then connected properly, so entering the capacitor and exiting from the other side, this noise was much lower. And this is not exactly a bypass capacitor, but it is a capacitor which is, or let's say it is shown how much of the noise can get through it if you don't connect capacitor properly. And that's what can also happen in your case, in case of bypassing. Let's say, for example, here, let me show it again. This is the connection of the 3.3 volts, and the 3.3 volts of input of this 3.3 volts comes here in the mid part. So what do we have here? This is the microcontroller taking noise from the power supply. Okay, this is the current source. This is the bypass capacitor. And now we take the power. This is the ground. Okay, the ground is connected here, but the power is coming there in the midpoint here. So this part of the inductance, this is this part here, would actually add to the noise because the noise is then flowing through this loop here. So this noise here, plus minus, minus plus, whatever, would add to the total noise that would then go conductively to this wire. So this actually happened here. Here it happened because of this short track here. The power came here. It ran into this capacitor. This short track here would then add additional noise because of the inductance of that track. Now, if this one would just connect this track directly to the capacitor, it wouldn't have any problems. But since it took the voltage away out of the diode, then this short track remained and added this enormous noise, decreasing it very efficiently by just connecting the capacitor correctly. So at the end, what you should be able to do, you should be able to choose the right capacitor technology for the bypassing application. And of course, you have 3 different capacitors for that. You have ceramic, you have aluminum electrolytic, and you have tantalum capacitors. So ceramic capacitors are those who should be placed as close as possible to the microcontroller or whatever you are bypassing. And then these are acting as a high frequency because, they are minimizing high frequency loops because they have the highest quality, the lowest ESL. The ceramic capacitors are therefore placed closest to the noise sources, let's say, to minimize the high frequency loop sizes. And then all the rest, let's say tantalum or electrolytic capacitors are acting as a bulk capacitors to minimize the impedance of the power supply at low frequencies, and also as a damping capacitors, which are lowering the quality of the parallel resonance frequencies which can occur because of the combination of different values of the capacitors, and of course the inductance of connections. You should be able to place correctly the bypass capacitors to all the components that require them in 2-layer and 4-layer PCBs. And this is a list of literature you can read to get any extra information about this matter. So at the end, what can I say? The bypass capacitor placement is one of the main techniques that every electrical engineer who is constructing PCBs should be very well aware of. And it should be like a routine. So the rule is, number one, every integrated circuit, especially the digital ones, require bypass capacitors. As many of these capacitors as the number of power and ground pins. The pairs of power and ground pin I'm talking about here. Because manufacturers, they are the only one who actually know what is inside the chips, right? Inside the integrated circuits. Because we did some calculations how to determine the value of the capacitance and how to determine the frequency range and so on. But the only one that really knows what is inside is the manufacturer. And therefore, they are preparing the ground and power pins for you to use them to place the capacitors next to them. Then they also state in the datasheets how many capacitors and what should be the value of these capacitors and the placement. So be aware of that and follow their instructions, because this would be the only way to finish your design properly. And placing these capacitors as close as possible to minimize all the high frequency loops that would then cause lower lower voltage fluctuations with that, and also lower radiation of electromagnetic interference.